All right, so in our last video, we went ahead and laid out a definition for Newton's three laws of motion, and all of them had to do with force. So let's talk a little bit about force and look at some examples of forces. So there's sort of two broad groups that I'm going to categorize forces in. Contact forces, where things actually touch each other, and non-contact forces, forces that sort of act from a distance. And then we'll look at a special third group that's not really a force at all, but you'll see that when we get there. So first, some contact forces. A few examples of contact forces. Well, the simplest of these could just be what we call an applied force. And that's you simply applying a force to something. That's directly pushing or pulling on something. If you walk up to a box and give it a shove, that is an applied force. And we'll have a lot of examples that are simply applied forces. Just due to the simplicity of it, it's very easy to write into a problem, and it just occurs naturally all the time in your everyday life. Another super common force that we will see is friction, and friction happens all over the place. You're probably familiar with friction as well, but friction is a force, and we need to treat it as such in physics. And what's special about friction is that it always opposes motion. So if something is moving to the right, and there is friction between the bottom of it and its surface that it's traveling across, if it's moving to the right, friction is going to point to the left. If it's moving upwards, friction is going to point downwards. Friction always opposes motion. Even if something's not truly moving, say if something's just sitting and you try to push it, well, if you can't even get it to move, that's because friction is pushing back. It's opposing that motion. I try to push my fist to the left. It doesn't move because friction is pushing to the right. Friction will always oppose motion. Another type of force you'll hear me refer to frequently, or any physicist, is a normal force. Now, this is not a normal force that, as opposed to the weird force. This is normal in the mathematical sense. Normal meaning perpendicular or at right angles to something. A normal force is a perpendicular force between objects. So whenever, I sit something on the ground or on a table, there's a force pushing up perpendicular to the table. If I'm standing on the ground is pushing straight upwards. That would be a normal force. But it doesn't have to be, it doesn't always have to be on the ground. I could push against the wall. And if I'm pushing against the wall is pushing me. That's Newton's third law in action. But that force from the wall is going to be at a right angle to the wall. We would call that a normal force. Normal to the wall, perpendicular to the wall. You could even push on the ceiling. And if the ceiling was pushing back at you, the force would be normal to the ceiling, perpendicular to the ceiling. That is what a normal force is. And we'll see them very frequently. Normal forces are very often part of Newton's third law, sort of the reaction force. And they also come up very frequently as a balancing force, a concept we'll get to at the very end of this chapter. A couple of other forces. Drag is something you might hear about or have heard about already. Drag is like friction, only sort of in three dimensions. Friction happens when two surfaces rub against each other. Drag happens as something flows through a medium. And that medium could be simply air. As something flows through air, there's sort of a three-dimensional friction. The air pushes on it as it goes through the air. Or if you're walking through water, the water pushes on you. If you're moving through some medium, anything except the vacuum of space, you're going to feel some sort of drag force. And since it is like friction, drag forces will also always oppose motion. So if you're trying to move to the right, trying to walk to the right through water, that water is going to have a drag force pushing you to the left. And the last contact force that I would like to cover is tension. Now, tension is special because it acts along rope or string or chain, whatever is tying some things together, but it acts in both directions, which can be a little tricky when you're setting up your problems. You have to be very careful how you label these things, because, for instance, if I pretend my pen is a piece of string and I'm pulling apart, well, on this side, the string is pulling to the right. It's pulling my left hand towards the right. But at the very same time, the string is pulling my right hand to the left. Tension acts in both directions. And because of this, you can use it to sort of turn forces around corners. If you have a pulley, for instance, with a string attached to it, you can make force go around a corner, which is kind of tricky and can cause some headaches at times whenever trying to deal with positives and negatives, whenever you're trying to determine directions on things. But I'll help you guys out with that once we begin working examples. You're going to want to label tension on a specific object. So back to my hand example, the tension on my left hand is to the right. The tension on my right hand is to the left. If we get specific about where the tension is acting, it definitely has a specific direction and will affect something accordingly. All right, so those are the contact forces. Now let's talk about forces at a distance. And really there's only one that we're going to deal with in this chapter, and that is gravity. Gravity comes from anything with matter. Anything with matter attracts anything else that is also made of matter, or mass attracts mass. And we'll look at the details of this later on, but it turns out that it's a very weak force in terms of small amounts of matter, or small amounts of mass. And in fact, we'll look specifically at the amount of gravity, the gravitational attraction between two people. And we'll see that it's very small. Really, the largest thing in the room or in the area is going to dominate gravity. And for us, that is Earth. Earth's gravity is the only thing that really has an effect on the things that we will study, in this class at least. And it's often referred to as weight. The pull of gravity is also referred to as weight, and I will make that distinction very clear later on. We're going to look at the difference between mass and weight, things that seem very closely related, and they are, but they are certainly not the same. Other forces at a distance that we will eventually study are the magnetic force and the electric force. We'll get to those later on, but that's in our last unit, the last couple of chapters for this entire semester. So I don't want to get too deep into those right now. But we'll get to see, by the time we finish up this whole class, that all of these forces at a distance act in a similar way. All right, well, what's left is imaginary forces, and just like the name suggests, they're not real. They are imaginary, but your brain can still think it feels them. And that's why I say beware of imaginary forces. Imaginary forces come from non-inertial reference frames. Well, what's a non-inertial reference frame? Let's start by defining an inertial reference frame. An inertial reference frame is one in which Newton's first law is valid. That is, that an object at rest will remain at rest, and an object in motion will remain in motion, moving in a straight line. That is, its velocity remains constant. So, reference frames with constant velocity themselves, including v equals 0, that means a stopped reference frame, are inertial. So the stopped one's pretty obvious. Obviously, if you're not moving, you would expect Newton's laws to behave. One where you might not expect it is a constant velocity. But you guys get an opportunity to test this all the time, probably almost every day. If you're, say, riding in a car at a constant velocity, do Newton's laws maintain their validity? Well, the answer is yes. So if you're just driving in your car at a constant velocity, anything that's just sitting around in your car, if it's at rest within that reference frame, it remains at rest. Things don't just start moving in your car while you're driving down the road at a constant speed. In fact, you can even throw, a ball up in the air. It will come right back down and you can catch it in your hand. I used to play around with this as a child. Maybe it's because I was destined to be a physicist. But it kind of baffled me. Okay, we're moving 60 miles per hour. Why, if I throw my, stuffed animal up, does it not just come slamming into my face? Well, the answer is that it too is moving at 60 miles per hour. We're all moving together. So whenever I throw it upwards, well, I've made it go up and down, but our side-to-side motion was the same all along. And now you might be asking, wait a second, but when I slam on the brakes, my cell phone goes flying out of my lap and, whatever's in the seat next to me goes everywhere. That's accelerating. Accelerations cause non-inertial reference frames. An accelerating reference frame is not inertial, and that's where imaginary forces start to appear. And remember, an acceleration is just a change in velocity. It could be a change in your speed, but it can also be a change in your direction. So, whenever you slam on the gas and you feel like you're being pushed into your chair, into your seat, yes and no. There are forces that are applying to you. Really what's happening is that the car is beginning to accelerate around you. And then the seat moves into you and then applies a force and accelerates you as well. And you feel that force from the chair is very real. But it feels like you're being pushed backwards. You're not being pushed backwards, you're being pushed forwards and it being accelerated forwards. That imaginary force would be the idea that something is pushing you backwards into your seat. Nothing is pushing you backwards when you slam on the gas. You're being pushed forwards, and it makes you feel as if you're being pushed backwards. Similarly, whenever you take a turn, if you're driving in your car, you don't hit the brakes very much, and you decide to take a sharp turn, say you turn to the left. Well, it feels like you're getting thrown to the right. But that's an imaginary force. It's because of your reference frame. Your reference frame is accelerating. It's being accelerated to the left. Its position is changing. The direction of your motion is changing. And so as that box that is your car moves to the left, you inside it think you're going to the right, but you're not really. That's an imaginary force. All right, well, other than being aware that they exist and making sure you don't add them into problems where they shouldn't belong, imaginary forces won't really play a role in our classroom. I'm not going to have you compute imaginary forces because they're not really there. They're imaginary. And studying accelerating reference frames is a topic that is a little more complex than we're going to deal with here in Survey of Physics. But I hope this gives you guys an idea of what forces are and what types of forces we will be dealing with in this class. So next, we will be taking a look at the formula. Well, really, there's, maybe you could call it formulas with an S, but really there's one big formula from this chapter, and we'll be taking a deeper dive into the force of gravity. So see you guys soon.